Hello friends, this is Sanyam. Today I'll be telling you about the minimization problem using the Simplex method. You've already learned about the maximization problem. I'm assuming that. One of our videos have already been posted regarding the maximization problem. The minimization problem is done in a similar way, except a few things here and there. Now, what you have in the screen in front of you is a minimization problem in which you have to minimize the cost. The objective function is 5x1 plus 6x2. And the constraints are x1 plus x2 is equal to 1000, x1 is less than 300, x2 is greater than equal to 150. Now x1 is less than equal to 300 lb and x2 is greater than equal to 150. Now in a maximization problem, you might have seen constraints less than equal to constraints. In this constraint also we'll add a slack variable s1, so it becomes x1 plus s1 is equal to 300. But in a minimization problem, you might have there'll be other constraints like greater than equal to. It doesn't mean that they can be greater than equal to constraints in maximization problems also, but I'm not sure if you might have faced them yet. So what we do in a greater than equal to constraint is we add a surplus variable as well as an artificial variable. So in order to make this inequality equal, what we do is we subtract a surplus variable first. So x2 minus s1 is equal to 150. But what we need in a basis solution, while we make a simplex matrix, if we take s1 as the basis variable, then the coefficient of s1 will be -1. But in a basis solution, what we need is an identity matrix. And in an identity matrix, all our coefficients should be 1 or 0. So in order to get that positive constraint, we add an artificial variable, which we will try and eliminate it in the later steps. So what we do is we'll change this equation to x2 minus s1 plus a1 equals to 150. So yeah, so the three equations we have converted it into equalities. So the first inequation was x1 plus x2 is equal to 1000. So the equation, there was no inequality out here. The equation was already having an equal to sign. In such kind of equations, what we do is we add an artificial variable only. We do not add a slack variable, or we do not add a surplus also, but we add only an artificial variable. That's why our first equation is x1 plus x2 plus 0x1 plus 0x2, 0 because there is no slack or surplus variable out here, that's why the coefficient is 0 in this case, plus a1 plus 0a2 again. Now these three variables, we've taken these because these three variables are used somewhere in the other constraints. That's why you just have to take note of these variables, but the coefficients will be 0 out here. The second equation was x1 is less than equal to 300. Now this is a less than equal to an equation, that's why we'll add a slack variable, that is s1 out here. That's why the coefficient of s1 is 1 out here, and other coefficients of other variables is 0. So this was the less than equal to constraint. Now the third inequation was greater than equal to constraint. That's why we've subtracted a surplus variable s2, and we've added another artificial variable a2. So because we subtracted the surplus variable, our coefficient is -1 out here, and we've added a artificial variable, that's why the coefficient is +1 out here. Now what I was telling you before was there's a negative sign in front of a surplus variable, that's why we cannot take this as the basis. Now the three equations which will form the basis, the three variables which are going to form the basis will be a2, s1 and a1. So what you can see is a1, in case of a1, there is the coefficient of the first inequation is 1, and then there will be 0 0. Similarly with a2, 1 0 0 and s1 0 1 0. So these three are forming a identity matrix in this case. Okay. So friends, our objective function was 5x1 plus 6x2 only, but because we've taken other variables also, that's why we'll have to add those variables in our objective function. Now the coefficient of s1 and s2 will be 0, just like in case of maximization problems which you might have done before, but we've taken the constraints, the coefficients of a1 and a2 as m. This is done in order to eliminate a1 from a final solution. What we need out here is, we need to minimize the cost. M out here will be, we are assuming m to be a very huge number. What this will do is, even if we have one value of a1, even if we have 1 unit of a1 in a final solution, the cost will go up to a very high level because the value of m is very high. So in order to rectify this mistake, automatically our simplex algorithm will eliminate a1 and a2 from a final solution. That's why we've added ma1 plus ma2 out here. Thank you. So now we've put all the values in a simplex table. I'm assuming from the very beginning that you're already done with the maximization problem. So just in a similar way, we've put in all the values in the simplex table. Now what we do in a maximization problem is, the entering variable is the one which is the one with the maximum positive value in the Cj minus Zj row. For a minimization problem, what we'll do is, we'll take in the value which is the most negative. Now the value of m we are assuming to be very high, so automatically minus 2m will be a very low value, will be the most negative value in this case. Minus 2m will be lesser than minus m. It will have a greater negative value than this one. That's why we'll take this as the pivot column. We'll take this column as a pivot column, and we'll assume x2. We'll assume x2 to be the entering variable in this case. So this is our pivot column, and what we did in a maximization problem is, we used to take out the ratio of 150 by 1, 300 by 0, 1000 by 1, and the least ratio should be would be a pivot row. This is also done in the minimization problem. So the least ratio in this case will be 150 by 1. 150 is lesser than 1000 by 1. So 150 is the least ratio. 300 by 0, we will not take this ratio because 0 is there in this place. That's why the pivot row will be this row, third row. So this is a this is a initial simplex table. Now this will be the leaving variable, this will be the entering variable. So in our next table, what we'll have is, instead of a2 out here, x2 will come out here. So doing all the calculations, doing the row transformations, I'm assuming you already know it because you've done maximization problems. We land up into this simplex table. This is the second simplex table. What you can see now is, instead of a2 out here, we have x2 in this row. So again, similarly we'll calculate Zj and Cj minus Zj, and again the least value in the Cj minus Zj, the most negative value, we'll take this as, we'll assume that column to be the pivot column, and the least ratio will assume as to be the pivot row, and we'll carry out transactions in a similar way until we reach upon a final simplex table. So that was a second simplex table. Now carrying out to there will be a third simplex table also, and now I'm showing you the final simplex table. This is the fourth simplex table. This is an optimal solution. Why is that so? Because Cj minus Zj row, all values in this row are positive or greater than or equal to 0. So 0, 0, 1, 0, m minus 6, m is a very large value, so automatically this becomes positive, and m again. So this is all the values in this row are positive. That's why this is a optimal solution. The value of z will be 5700. That is 5 into 300 plus 6 into 700 equals to 5700. And the value of x1 and x2 will be x1 equals to 300, x2 equals to 700, and s2 will be equal to 550. So this is a final solution mix. Now in this table, if we have to do sensitivity analysis, so one thing you should know, so in this final simplex table, what we can make out, just looking at the table, besides our z value and the optimal values of x1, x2 and s2, For the first constraint, the variable we added was S1. So basically the value of S1 in the Cj minus Zj row is 1 out here. This we call the shadow price. The value in this table is called the shadow price. The value in this particular cell is called the shadow price. So in our case, the negative of this value, I'm sorry. So -1 will be the shadow price of the first constraint. Similarly, A1 and A2, 6 will be the shadow price in the second constraint, and 0 will be the shadow price in the third constraint. We out here we ignore m, the value of m out here, and we'll only take 6, negative of -6, that will be 6, and 0 will be 0 in this case. That's it. Thank you. Now for post sensitivity analysis, what we are doing is question number 37 in our book, chapter the spiral which sir gave us, the question from that. So you should go through the problem first. It is said refer to table M7.6, which is the optimal table for the Flair Furniture Company problem. The first question in this problem is, what are the values of the shadow price? So in this question, shadow prices will be the values in the Cj minus Zj row corresponding to S1 and S2. So in S1 the value should be 5, and S2 the value will be 15, negative of -5 and negative of -15, which comes out to be 5 and 15. That's why I have taken the shadow prices as 5 and 15 for the two constraints. Now the second question is, interpret the physical meaning of each shadow price in the context of the furniture problem. Now shadow price, what it basically means is, if we had one resource extra of S1, that is one resource extra of constraint 1. Our constraint 1 is out here, table or chair, I'm not sure, but whatever constraint is, if the first constraint is related to tables, so nikal. I'm sorry friends, but my mistake. The first constraint was painting hours and the second was carpentry hours. So basically shadow prices, the inference of shadow prices is, if we increase 1 hour of our painting hours, then our value of then our profit will increase by what amount? So if a shadow price is 5, so increasing the painting hours by 1 unit, our profit will rise by 5. Now again, what I showed you out here, the shadow price was minus of -5 and minus of -15. Please do not get confused by delta, because this delta is I've added this delta in order to solve the C part of the question. So the final solution does not contain this part. That's why if you have any confusion, you can go through the final optimal solution, which I haven't drawn out here. Now coming to the C part, the C part says, what is the range over which the profit per table can vary without changing the optimal basis, that is the solution mix. So the literal meaning of this question is, how much can we vary the profit per table. The profit per table is 70 in our final problem. So if we need to change the value of 70, to what extent can we increase it or decrease it? So in order to do that, we add a variable called delta, 70 plus delta. We are assuming now we are going to find out the value of this delta. Now because this table is a part of our optimal solution, so we'll write down this cost 70 plus delta out here as well. So now calculating Z after adding delta will be 70 plus delta into 1 will come to be 70 plus delta. There will be no effect of delta in this one, because 70 plus delta into 0 is 0, plus 50 into 1 will be 50. Similarly we'll so we'll calculate the new values of delta, new values of Z, I'm sorry, using 70 plus delta into 1 out here, then 70 plus delta into 0 plus 50 into 1 will be 50. Similarly for this into this plus this into this will amount to this, this into this plus this into this will amount to this. So we have our Z values. Now we'll calculate the Cj minus Zj values. which will amount to 70 plus delta minus 70 plus delta will be 0. In this case as well, 50 minus 50 will be 0. In this case, our values will be minus 5 minus 1.5 delta, and for S2 it will be minus 15 plus 0.5 delta. Now, as this is a maximization problem, so this is a maximization problem. So for optimality, what we assume that our values for all the elements in Cj minus Zj row should be less than or equal to 0. So in order to satisfy that, we form two inequalities. We assume we'll take out the values of delta pertaining to this this value being less than or equal to 0. So we've written out minus 5 minus 1.5 delta is less than or equal to 0. Similarly, we want this as well to be negative, and so we'll find the range of this delta according to that. So we have written 0.5 delta minus 15 is less than or equal to 0. Solving these two inequalities, we get delta is greater than or equal to minus 1.5 and delta is less than or equal to 30. So so basically our initial profit for one table was 70. So if we add that 70 minus 10 by 3, 10 by 3 is coming out from delta is basically the lower bound of delta out here is minus 10 by 3 and the higher bound of delta is 30. So if we add if we subtract the lower bound, which is 10 by 3, so it will amount to 70 minus 10 by 3, and the higher bound is 30. So we'll add the higher bound, 70 plus 30. So a range for the value profit of one table comes out to be 66.7, from 66.7 to 100. So this is the answer for the C part of this question. So now we'll go for the D part of the question. What is the range of optimality for C, number of chairs produced? What we did in the previous was we added delta above in this to 70. In this case, similarly, we'll add delta to the coefficient of chairs in our profit function. So we've done 50 plus delta. As C is in a basis solution, that's why we'll write 50 plus delta out here as well. And in a similar manner, we'll calculate the value of Z for all the variables, and we'll calculate Cj minus Zj. Again, to calculate the range of delta, what we'll do is we'll simply validate both of these values to be less than or equal to 0. So we've got these two equations again. 2 delta minus 5 is less than or equal to 0, and minus 15 minus delta is less than or equal to 0. Solving these two, we get the delta to be less than or equal to 2.5 and greater than or equal to be minus 15. So the range of delta is minus 15 to 2.5. So adding these two values in the initial coefficient of profit for one table chair is what you get is 50 minus 15 to 50 plus 2.5. So a range for profit of one unit of chair is 35 to 52.5. So for this range of profit of one chair, solution mix will not change. We come to the E part. E part has been done over here. What I explained earlier was D part, which is here. So do not go to this part. So E part, the question is, how many hours can flare furniture add to or remove from the first resource, painting department time, without changing the basis? So our first constraint, S1, the variable we added, was pertaining to the first constraint, right? That's why what the values when we need to calculate the RHS, I'm sorry, not RHS, when we need to calculate the range of a how many hours can flare furniture add to or remove from the first, when we need to when we need to know that how many hours can be added to the painting or subtracted from the painting, what we'll do is we'll simply find the range of 30 by 1.5 and 40 by minus 2. Why 1.5 and 2? Because S1 is the variable pertaining to the first constraint. When we had the inequality, what we did is, in order to make it, in order to convert it into a normal equation, we had added S1 in the first constraint. That's why S1 is the variable pertaining to the first constraint. That's why we'll take the values corresponding to the values in the S1 column. So what we did is, over here is 30 by 1.5 and 40 by minus 2. The values come out to be 20 and minus 20. Now in this question we only have two constraints, but supposingly if we had more than two constraints, so we would automatically be having more than two ratios. So out of these however number of ratios are there, we'll take in the least negative and the least positive value. The least negative value will be we'll add the least negative value to our initial resource. Our initial resource for the painting was 100, which was given in the initial problem. Our first constraint, the initial problem, we had 100 painting hours. So what we are trying to find over here is by how much amount the painting hours can be increased or decreased in order to have the same basis solution. So out here what we did is the least negative value is minus 20. So we've just taken this value 20, we've ignored the sign 20, and we've added to a right hand side, that is 100. So 100 plus 20, that will be a upper bound, and the least positive value, in this case it's 20. So we've subtracted 20 from 100. So 100 minus 20 to 100 plus 20. Now you might be having confusion over here because the values of both these two are 20 and minus 20. Supposingly if the value of this was minus 30, so we would have added 30 over here and not subtracted 30 from here, just to make that more clear. So if there was minus 30 over here, minus 30, so a range would have been 100 minus 20 to 100 plus 30. That would be 80 plus 130. In this case, however, it is 20 and minus 20, so our range will be 80 to 120. So 20 hours can be added or subtracted to our painting hours in order to have the same basis solution. So now coming to our F part, conduct RHS ranging on the carpentry department resource to determine the range over which the shadow price remains valid. Now before this, in the E part we had calculated the same range for the painting department. Now we are doing the same for the carpentry department. So the carpentry department was the second constraint, and S2 was the variable pertaining to the second constraint. That's why in this case we'll find the ratio of 30 to minus 0.5 and 40 to 1. So I've calculated it over here in the F part. It is basically 30 by minus 0.5, which will be minus 60, and 40 by 1, which is 40. So the least negative and the least positive, as there are only two values in this, so we do not need to compare any values. So the least negative, which comes out to be minus 60 itself, if there would have been another ratio that is minus 100, so the least negative in this case would have been minus 60, because minus 60 is 60 is basically less than 100. That's why. So minus 60 would have been the value in that case. So for the range, we'll do what we'll do is we'll add 60. We'll add the lowest negative, again I'm repeating, the lowest negative to the initial resource hours, how many we had. So initially we had 240 hours in the carpentry department, so we'll add 60 to that. So the upper bound will be 240 plus 60, and similarly we'll subtract 40 from the initial number of hours, that is 240 minus 40 for the lower range. Again I'm repeating, we'll subtract the least positive value and we'll add the least negative value. So our range comes out to be 200 to 300. In the post sensitivity analysis, I think we've covered all cases except one. So in order to tell that, I'm using another question. So I'm just showing you the final optimal solution for a certain problem. And now in this optimal solution, x2 is not a part of our basis. So basically what we in the previous question during the post sensitivity analysis, what we were finding out was profit, the range of profit, how much we can vary it. In this case also we'll try and find out the range of profit for the variable x2 for which our solution basis does not change. So in this case x2 is not a part of the basis, so x2 is a non-basic variable. That's why when we try to find out the profit range for this one, so that our solution does not change, there will be a different method for that. Now in regards to that, even if we add delta out here like we did in the previous case, that 30 plus delta effect would not come out here because x2 is not there in the basis. So what we'll simply do is in order to verify that our solution does not change, solution basis does not change, we'll just see the same, we'll do the same steps as before. We'll ensure that Cj minus Zj value, all these values are less than equal to 0. So for x2 we need to calculate for x2, that's why we'll do Cj minus Zj for this value should be less than equal to 0. So Cj minus Zj is less than equal to 0, that I'll do. So regarding that, I've done Cj minus Zj is less than equal to 0. So basically it turns out to be Cj is less than equal to Zj. Cj is less than equal to, now Zj, I've simply put the value of Zj in this. This is a very easy question actually, for when we need to find out the range for the profit of a non-basic variable. It is fairly simple. Cj should be less than equal to Zj. That is in case of a maximization problem. If it would have been a minimization problem, then we would have done Cj minus Zj is greater than equal to 0, and Cj would have been greater than equal to Zj. So in this case, Zj was coming out to be 40 from our optimal solution. Hopefully whatever I've taught in this few minutes, hopefully it will help you all. If you have any other doubts, you can ask me personally. My name is Sanyam, I'm from section D. Otherwise, I'm sorry if you did not understand any part of this, but I tried my best in this. Thank you, thanks a lot.